Okay. All right, guys, can you hear me and also see my screen?
Yep, we can.
Yep.
Okay, so let me just get everything set up. More chat. I'll take the chat. All right, so welcome to this session on AN work exercise 3, and so for this, I think what we're gonna do is, so this exercise basically has 3 parts. So first one is PCA, and then, well, PCA, this exercise actually, I think it's a part where you have to write your own code, and you have to, write some code, and there's not too much. You need to kind of like figure out how you're gonna implement this with those kind of instruction. So we will probably spend the most of the time on this session on this, just to, well, I will try to share my code, and then let's say if there are some mistake or also mistake on it, so you guys can help me to verify it as well. And then second one, stock at Autoencoder. Well, this one is actually, well, you just need to basically go through kind of like a documentation. So because the code has already provided, so you basically just need to understand what is going on, and then, well, you need to modify some parameters, and then you need to answer some question, let's say. We will try to see if there are some question that we can directly answer. And let's say which part we need to do it, in our own time to experiment to get the result. And the same goes for the convolutional neural network. It's also you need to actually run through this CNN exercise, basically this script, and trying to understand what is going on. And after that, you actually need to kind of like figure some information which is inside of this CNN network. And also you want to try, maybe you need to try to run a small CNN on this CNN digits, and then you need to basically again try to try some parameter changes and see what kind of result you're gonna get, and we need to discuss it. And yeah, basically the report is about these 3 parts. So that's basically the whole structure. So let's get started maybe with PCA. Okay. So I don't want to go really. I think you guys already have pretty much go through this document. So so here I'm not gonna just I'm not gonna explain this. Okay. But this one is pretty basically is like the step when you want to do a PCA. You want to implement basically a PCA algorithm. And first thing you want to exercise is, well, this one you don't have to do it in your report, but it's a good exercise to get you started. Okay. So it's first you want to build some script which is actually trying to do a PCA on the random data. So it's just something you totally generate from randomly. So if I create this live script. I think the live script is actually good to is very good to illustrate, because you can just run it by sections. And so here you are just saying, okay, here is basically just generate the random data in a matrix with a parameter of p and n, and p stands for the dimension of that vector, and n stands for how many data points you have. Okay, and then you get this x random, which is, well, basically your input matrix, and you will calculate the mean as well, and after that you use this convolute function which you use to calculate the covariance matrix of the input data. Okay, so that you can go ahead and continue to calculate the eigenvector and also the eigenvalues. Okay, And so actually, I don't know who asked that during the last session. Actually, I want to respond to one of the questions which we asked in the last workshop. So I don't know who asked for it. I mean, I don't remember her name now. It's basically asking like in the last workshop, we're doing the data normalization, and we are wondering why we are normalizing just like calculating the mean value of the training data. Why we are not computing using both the whole data, which consists of both training and also the test data. I found some after that I found a resource about it. It's basically I think it's, I don't know if I put it somewhere here. It's like I think it's here. No, it's not. Okay, so I don't know if you guys remember this question about why we are only training data on for scale when we are trying to scaling the data set. So there's basically so when you are scaling the data, only use the training set for the fit, don't involve any test data set. So basically the idea is that if you're normalizing your data set, when you are normalizing your training set and you included the test data, it's like kind of like it's not in the real life situation. So basically in your life situation, you should when you are normalizing your data, you have no idea what your test data is. So if you are doing that, it's like you are basically cheating. So you don't want that. Okay, so this is the response to the last workshop question we have. So this is just I don't know, I don't know who asked that. I mean, but I remember it's a girl. But
wasn't it Iris?
No, I don't remember her name, but no, I don't remember. Something with an M, but she's not here now. If I
okay.
see her in the chat, I will give the response too.
Okay. Yeah, maybe we will later on just like post something in the WhatsApp group and just saying that we found some information to support that argument of like.
Yes.
Okay. All right. So well, I don't know. So I'm gonna quickly run through this live script. So here here just like first you prepare your data and you basically you calculate you generate your random data and you calculate the mean here just using this command, and then you use this Ahen function to calculate your related Ahen vector and the Ahen values. And here what I did
Neil, here. Can I shortly interrupt for something?
Yes, sure. Go ahead.
Actually, what I did for taking the mean, I took it twice because you have like the 50 dimensions. So first I took the mean of that, and then by just using the function mean twice, I finally got just one result for the mean of x. So here we are obviously using something different. And I'm not sure which of both approaches is correct.
Yeah, so I don't understand. So you're basically taking the mean of the whole, let's say the X random, right? So you are getting the mean for 50 times 500, right? So you are like taking the whole mean of that.
Yeah, so first I get actually 500 means, then I take again the mean of these 500. So there is a difference whether you look actually at all the 50 dimensions of all the 50 multiplied with 500, or you take the mean of that, or you take the the mean of really everything, obtaining just one value.
Okay, I understand your question right now. Okay, let me try to. I understand what you mean, but I will try to answer this. Why we are so here? What I did here, I'm actually taking the mean of 50 points, data points. So I think if you want to imagine here, so basically P is basically your input. Like you have like X, let's say X1, X2, X3 until X, in this case until X500. Okay, so you cannot just imagine this as an input vector. Okay, but I mean in this case, I mean it's well, we're just testing some random numbers here. So well, it's just basically something between 0 or 1, whatever. Well, doesn't mean anything. But in real life, it can be mean like multi-dimensional input data. Okay, so for example, let's say you want to, let's say maybe it's this dimension data is a person's information. For example, the person's like the weight, like some healthy data like the weight and the length, or like those kind of data. And and each data takes one, it's one element of the vector. So when you are trying to compute the mean, so of course you don't want to mean both. We don't want to take the mean of both the weight and also the length, right? So you also, so you just want to take the mean of all the lengths or all the weight, and you don't want to just like, because those kind of vectors, you can it can mean different, totally different type of data. Okay.
Yeah, you're right. Yeah.
Right.
Thank you.
So that's why we are just taking the mean of. So basically, we are just taking, because we only have like 50 data points here. So we are taking the average of the 15 data points. Okay.
Okay. Thank you.
All right. I hope this is clear. Okay. So let's continue. So here, calculates the eigenvalue and eigen. Okay. So we just use this function and you get your eigenvectors and eigenvalues. Well, I'm not going to explain too much about eigenvalue and eigenvectors here. So you just this is behind some, there are some mathematical of linear algebra behind this, but yeah, but I'm gonna not like try to explain here. It's just something you understand. Okay, so it's kind of like you can imagine those kind of two things. You can use those kind of eigenvalue vectors or eigenvalue to actually reconstruct your like they store some information for the matrix, so you can use these kind of vectors and value to actually reconstruct it. Okay. So here, so once you get your, okay, maybe did I run this? I didn't run this. Okay. So you can maybe here you can already take a look. What does this like the like this vector looks like, or this eigenvalues looks like? So you can just basically, yeah, you can just take a peek at these things. So here is just, well, here the so here this is the vector. This is the eigenvector. Okay, but it's, so actually it's, I think each column, right? Each column stands for one vectors, and also this D random vector stands for the eigenvalue. So if you take a look at this, so you see here the eigenvalues here. Okay, so it's in this diagonal, in the diagonal of this matrix. Okay, so basically if you go back and you just everything is 0, just like the one on the diagonal like direction, you have some value, which is of course, and which is your eigenvalues. Okay, so what are you gonna do here? Then you want to actually collect this eigenvalues, so you use this function, and then you basically just saying, okay, I'm just gonna collect the values in the diagonal and I'm gonna put it in one array. And here, what I did, I just used a kind of like sorting method here, just sort the eigenvalue, this array by descent. So the biggest come first. So if I take a look at this eigenvalues right now, so it's basically just an array and starting the biggest one until the smallest one. Okay. So what are you gonna do here? So here, if we go back to this exercise, and here they are asking you, okay, this is basically the step. So here there's one crucial part, let's say. So you need to determine the dimension of the queue of the reduced data set. Okay. So what I mean, so basically the idea is that, okay, first in the beginning, your input vector has 500 dimension. So what are we gonna here? We're gonna actually reduce it to a dimension so that, you know, like so that we can really reduce the size of the matrix. And you need to decide how much you want to reduce, how much because in the beginning we have 500, and you need to decide how much to reduce. Okay. So one of the criteria here is basically you need to determine the dimension of Q of a reduced data set by looking at the largest eigenvalues. Okay. And the quality of the reduction depending on how close the sum of the the largest Q eigenvalues is to the sum of the P eigenvalues. Okay, I know I don't know whether this is confusing for you guys. So basically, if I explain this very intuitively, so basically here, because you see my eigenvalue, I already sorted out. So what does it mean? Like first, the sum of the all P value, that's easy. You just sum like all those 500 things up and you get the sum of the P. So you want to choose a Q, which is actually the sum of the largest Q. So that's starting from here. If your Q is 1, then your sum is just this value. And if your Q is 2, and this value plus this value. Okay. So you want to choose a dimension which is the sum of the Q largest data like eigenvalue is pretty much the same as the sum of the P. So if you look at this, well, here is like 16, and this is, and suddenly we see a very short, like very significant drop here. This is 4, and now this is somewhere close to 0. So in this case, so in my case, I would just choose, okay, this is 49. So I just choose the like number of 49. So I just use Q at 49, and then you're gonna get this up right after your decide your Q value. So you need to construct this projection matrix ET. So later on we're gonna use that for the real compression. Okay, so once you set it down with the Q, so you want to find, okay, the actually, so you're gonna get Q 49 eigenvalues. So how do you gonna construct this ET? Is actually you just how do you say? You just actually need to find the corresponding eigenvector for those largest eigenvalues. Okay, so that's why I did this index here. So I just basically say, okay, just ET, just and I just give the index saying that, okay, I need this is from the vector of the eigenvector matrix. So I'm gonna grab all the column. Wait, the rows. Okay, and I'm gonna choose the top. I'm gonna choose the index of the top like Q values basically. Okay. So there's some playing around because this is also I just playing around and just find out, okay, I need to do some, like transpose here and transpose there. So this is basically by trying to get the dimension, because you know that in the end your ET is going to be a Q times P. Okay, so I just run this. Let's just try. I mean, the thing you want to just to verify is that your dimension of your ET. Okay, so ET here is 49 times 500. So well, which is correct according to Q times P. And yeah, so basically you got your ET now. So now you can use this ET just time with your original data matrix, and you get your reduced one. So if I just run this, so your X random reduce is gonna be 50 data sets. Now you have a vector of 49 instead of 500. Okay. And then you can use this ET matrix to reconstruct your reduce the matrix. So you just basically some matrix modification like matrix modification again, and you did this. And of course, don't forget to add your mean. And then after that, you get your X random reconstruct. And of course, you want to, like after this kind of compress and reconstruct, you want to, see, did you lose what is the difference between your original and your reconstruct data? And you just, then you just do this kind of RMS calculation, and then this is what you get. Okay. So I don't know if you guys get to the similar values here. So for me, I think it's quite small, so pretty reasonable, I would say.
I had a quite large value actually with this one in comparison with then the one on the handwritten digits. There I had really a low value. But the RMS, I think I wrote it down somewhere, was something like 0.5 or more. And when I took more cues, more principal components, it went a bit down, but it was really not a good result.
And what is your select your Q values?
Let's see. It was something like 10, 20, 30, 40 I took. But it might have been something in the script that was not correct also. So I will have to check it again.
Okay. But do you understand the process, like the idea? How did you actually choose the Q?
Yes. Yeah.
Okay.
Yeah.
Okay.
Thank you.
Right. So I think this part is kind of tricky to actually construct the ET. So because now I'm also kind of confused why I'm doing this. But anyway, I thought it's something, but I think what I did, I actually checked whether my ET, like this projection matrix, is actually, I kind of like checked like this one very carefully, and then yeah, but I did the transpose on this, so yeah, probably right. All right. So any still more question on this part, on this first exercise with random data? No.
Looks good.
Okay. And Aries, don't worry. So after this session, of course, as usual, I'm gonna put this script somewhere in the Notion page, and you guys can find it just to check. And if you notice any issues, you can just always comment on the Notion page or just send me a message. Okay.
Thanks. Yeah.
Okay, let's continue. So well, next one is basically, yeah. So now you are not doing, now you are just not doing the random data. You're gonna load this data file, these things, and I think I have something pretty much the same. Well, you just actually, you just like when you load your data, I just basically, yeah, I just kind of like modify a bit, and the rest of the stuff is pretty much the same. But of course, I'm gonna observe this Q things here. So the Q equals 4 looks nice. Oh, but I'm just quickly run this to see what is going on, just to make sure it was correct. Yeah, it's pretty much the same procedure. So now let's come to the Q equals 4. Why did I did that? So let me take a look at this eigenvalues. Yeah, so well, yeah, actually just the first four seems to be very large. But and here is already yeah, but here is already this is like 0, 0, 0, 6, right? Okay. I think here, yeah, this is same level. Well, maybe here you can try with Q equals 2. Maybe it's already good, but here, well, this is just because I was seeing this E symbol, so I just get it here. So yeah, so basically this one you can, I don't know, so I just pick it 4. So let's see what happened. So eigenvalue is 4. So I just run this. The code is exactly the same. It's just like the beginning part is different. Okay. And here, yeah, the RMS doesn't change at all, and it's about 0.3. Okay. So and here they're asking that how does this reduction of random data compares to the highly correlated data? So I mean, from what we've observed, so actually the reduction of random data is much more like giving less error if you do it with highly correlated data. So it's it's doing much better in the random data. Okay. But anyway, but you don't have to write this report, just something I just say it. Okay. This is not in the report. But anyway, this two exercises is very good for you to understand how do you actually implement PCA. So if you take a look at the let's say the handwritten digit. So now I think it's gonna be easier for you to write the code. Okay, so here you just need to basically follow the instruction here of these steps and try to answer some questions. Okay, let's go right into this code. Okay, so here, so basically what you're gonna do is you need to load some, this tree is a mat, and then it's just basically an image. Okay, but it's a green image, and like I said in my OpenCV tutorial, the green image is basically green image is just a matrix of two-dimensional matrix, and the value in each pixel it stands for the how white or how black you're gonna be. So so yeah, you can just basically treat it as like the exercise we did before. Okay, so here you want to do what is the first step? So you just compute. Okay, so here's introduce some command which you can actually visualize the images, and then so now here we are just actually loading a bunch of street, like we are loading a bunch of like data of tree, pictures of the tree. So let's just quickly run this. Okay. So here I just run the first block. So it's basically telling me, okay, how many the tree. So it's actually in this data set, it's actually you have like 500 pictures. Huh? Because you see your dimension of your length and width is 16. So which is times together, then it's 256. So actually in this data set, you get 500 pictures of tree. And here I'm just saying the number 15 pictures. I'm just visualize here. Okay. And here again is asking to compute the mean of the tree and just display it. So you can see here I just use this mean command again. And like I said, you can just directly use it because your number of the data set is 500. So and you just So what after you run this, your mean tree is just gonna be an image, and it will look something. It will look something like this. Okay. And yeah, does anyone actually know how to actually clear this kind of like this plot here? Because I was trying to, you know, like trying to get rid of this just to show something new, but it's, I don't know how. Okay. So again, so this is your mean, basically. Your mean image looks like. And what else you want to do? So you compute the mean and deflate it. Take a look of the command. Okay, you can just take a look. So you know what does this mean tree looks like. And then again, you need to compute the covariance matrix of the whole data set of 3S. Okay. And here there's a note here saying that's actually the cove function, the covariance function actually. So you already actually subtract the mean automatically, so you don't have to do this before that. So yeah, so you just do this, you just use this function, and you get your trees convoluted matrix covariance matrix here. And again, we are actually you know, and we are using this AHEN function to get the AHEN values and also the AHEN vectors of this covariance matrix. And this is also the, yeah, so compute this and also compute this. And you actually need to plot the AHEN values. Okay, so you just plot this, just run this, see what happens. And you basically get this kind of thing. Okay, so yes, actually, if you see this, actually the AHEN value is increasing a lot after, right after 200 values, 200 of the in the last two, let's say 50 AHEN values. It's actually a lot. So if you see this again, well, you are just gonna get this again. Okay, so it's pretty much the same until far.
Neo,
Yes.
I have a question here, because normally what you observe with the PCA, I observed it also with the numbers, is that even with a small number of queues, that let's say that when you got a small number and you go a little bit higher, then it decreases a lot. So I think it might be that we should just flip the curve. I will put it in the chat. But I applied flip it to the eigenvalues, and then you actually see the curve decreasing the steepest when you are adding just one or two or three queues, principal components, and it should decrease less the more components you're adding. So this is why we should flip it, I think. Maybe I'm not clear in how I try to explain it.
You mean like you want to show the you want to show like the biggest AHEN value in the beginning, or what do you mean by?
Yeah, because then you can really see how it goes down while you are adding more components.
Okay.
So let's say in the beginning you have 4 of them, and when you go up and go up, then the difference should be really low. Like when you go down in the matrix of eigenvalues, the values become so much smaller because there doesn't change a lot anymore. And then you have kind of this quality loss function, let's say, that shows the impact of even only 4 components. I will just type in the chat what I did there.
Okay. eigenvalues split times b. Okay, so I just copy your command and let's see what we got.
Yeah.
All right, but did I use eigenvalue in the below as well? But actually done math, right? Done math. All right, so let's say if you just run this and what we're gonna do, let's just plot, forget about this. You're gonna forget about this and just plot this eigen values. Huh?
Yeah.
Why is I? Okay, it's here. Invalid characters. Okay, I'm just gonna run this. Unsupported symbol. Oh.
I just a space, I think.
Okay, so is this what you mean?
Yeah, because there you can see how steep it goes in the beginning, and after that it doesn't become so much better. So this is normally, I think, how it should look like.
Mm-hmm. Okay. Yeah, that's yeah. It's I think this way is better for you too. So actually, you can choose your Q values later on very clearly. Okay.
Yeah.
All right. Good point. Okay. And so here, yeah, like I said, if you choose this, you can, if you see this graph, you want to actually choose when you choose your Q. So here I just choose the Q here with 50. So it's just, you know, like the first part. So that's what I choose for the Q. And here you want to actually, well, you want to, so after you choose your Q, you want to calculate the reconstruction error. So, so you need to actually write kind of function, which is try to compute the your reconstruction by using different kinds of different value of Q, and you need to collect those reconstruction arrows, and then you need to plot it, basically plot it. Okay. So for this function UO, it's basically what we did. Well, yeah, if you go to this function, so I'm just gonna say call it BCA. Well, what you're gonna do? Well, you just did this kind of, you just like, of course, you're gonna, you know, build your projection matrix again, and you compress it, reconstruct it, and you measure, and you return your like an RMS value for your reconstruction. So it's exactly the same what we did before. Okay, so here, so then you want to, well, what is this plot? What does this? Okay, so first you want to compress the data, projecting it to 1, 2, 3 for project principal element. So basically, yeah, you Q just, it just means like you just try with Q equals 1, 2, 3, 4, and then you want to reconstruct the images from those compressor and pull some pictures of the full reconstruction. Actually, I haven't did that. I haven't do this yet. So, but it's just a matter of like, okay, just Q equals to 1, and you just plot your images, and then Q equals 2. But I'm gonna maybe just do a small quick example here. Maybe just, I'm just gonna do a quick example here. So let's say Q equals to 1. And you wanna say, okay, I'm just gonna copy the code from here, because I think this is what I did before. Oh, you already did that. Okay, values. Okay, I think this one will not impact too much on my result. So Let's see here. Just gonna copy this. Okay, so here we're gonna define the AHIM values again, which is using the original the AHIM values. And here again, so here I just sorted it again as a descending order, and I choose Q, let's say equals to 1. So it's again the same stuff, and you just like then you just Q reduce and you reconstruct it, and you plot it. Okay, so here I'm plotting actually the 100, the number 100 images of 3. But here he's asking that what is it? Reconstruct images from those compares and plot some pictures of the 4 reconstruction. Okay, so here you just, let's say, so here is just, I think this one you can just choose any like numbers you want between 1 and 200 and 1 and how many pictures you got actually, how many trees? 500. So you can just pick any value between 1 and 500. And so let's just try to run this. And this is what you get with 100. Let's just copy this for a moment, put this in Notion somewhere. Okay, this is which question? Yeah, here. So this is Q equals to 1, and this is what you got. And let's change this to 2. Well, this is the same stuff. Yeah, because now I'm kind of confused which one. Yeah, this one is Q equals 2. Let me just rerun this just to be sure. Okay. This. And just out of curiosity, let's run it 3. Okay, so what do you guys think? So actually, I think the different one is like Q equals to 1 compares to the rest of the other images. Like the Q equals 2, 3, 4. That seems too much difference, I would say. It's just the one is actually, well, the shape is pretty much the same, but you see that there's kind of like the how do you say, in this part, the intensity is actually kind of lower than the rest of the images. Okay. So here, let's just see the original one. So here, just say, okay, if you just try to load this 100 in the beginning. Oh, wait a second. This 100. Okay, this is interesting. Well, okay. But this one actually looks pretty much like the average here, like the mean here. But anyway, this is what we observe this time. Is there any comment so far? Did you guys get the same similar stuff, or you have something different?
Yes, I had something quite similar. Just like with only one queue, we have already good results because we can already see it's a tree. So I think it really runs well with one principal component.
Mm-hmm.
And after that, it is just fine-tuned when you go up to 50 or more, but it doesn't change a lot anymore. That is at least what I got, and the first runs, they look similar to yours.
Okay. You mean like the
I
q
don't.
equals to 1? You pretty much get the same stuff?
Yes, yeah, yeah. I don't know how it was with other people.
Because what's interesting me, I think there's one very, if this picture is correct, because this is the original and like the 100 image, which is the street looks like this, and this is the mean, and this is what we actually get after like let's say q is already equals to 4 now, and this is what you get for your reconstruction. So you can see that actually the reconstruction images looks quite similar to the mean one instead of this like the original. Well, of course, you can still see you can still see it's a 3, yeah. But the thing is like I think it's the reconstruct. It might be an effect of this kind of compress and reconstruction. So you basically are very close to the mean instead of let's say like you are like kind of like your result is gonna be closer to the mean when instead of like just looks something like this. Yeah, just my okay, let me just maybe just try another one. Let's say try 10. And here it's also 10. Let's see. So this 10 looks like this. And this one is gonna be, yeah. Yeah. It's just like they are converging, you know, when you reconstruct, you are like more closing. You are like you like closing to the mean in the beginning, and then you just, you know, based on that, you can just based on your original image, you just add something more. Okay. All right. Anyone wants to comment on this? Because this is now getting quite interesting now. Okay, should I continue or what?
Yeah, for me it would be fine to continue. It makes sense what we observe, I think. So yeah.
For me too.
Right. All right. Okay, so next part is basically, well, you want to write a function. Well, that's what I did. I'm writing my PCA to calculate the error. And you want to basically plot a function which is reconstructing arrow as the function of the q. Okay, so you want to say, okay, what is the reconstruction arrow when the q is 1, 2, 3 until 50. Okay, so what I did here, you just q equals to 50 now, and I just initialize the reconstruction arrow as 1 times 50 vector. And I initialize everything as 0 in the beginning, and then just run a for loop. and then you see, okay, just now you just get your arrow for each value of q from 1 to infinity, and you just plot this. Okay, and let's just plot this, and this is basically what I got. So actually, you see that's actually when q is equals to 1, it's actually quite the arrow is quite small, and then right after that you get increased quite fast, huh? And then if you keep on increasing, it's dropped a bit, and then it's kind of like have some kind of oscillation here, and then you stick to kind of like a value like around 0.31 here. Okay, so this is what I've observed. I don't know if you guys observe the same things or not. Okay, let me just copy my plot here. Let me come. No comment on this. You are getting the same stuff.
I was not getting. I plotted it a bit differently, but I do think it's a bit weird that after 1 it goes up so much. I don't know what is happening there.
Yeah. But maybe let's put a figure. Let's put a figure to see what exactly is happening. Oh, I think I can just see the reconstruction arrow as vectors, right? So let's just take a look. Yeah, so in the beginning, q is equals to 1, you get this, and then you get 3, 4. Yeah, right after the q equals to 1, when you pick q equals 2, actually it's just like start to increase. You see the big leap, and after that it start to kind of like dropping and oscillating, and finally kind of like goes to this 3118, like 0.31. Yeah, so it's actually quite interesting. So actually the q, if you just pick the first one, it's doing fine, and then after that it's getting worse basically. So maybe this is a very good, interesting observation, because here, well, actually just choosing q equals to 1, I mean, that's the principle which we seeing before, which is not applying anymore. But I think this has to do something with, because now we are dealing with the image right now, and then this image has some pattern which is free. So it's not like it's different from what it's just from what we see before, like let's say the random one. Well, if you put a random matrix as an image, well, it's just a bunch of noise. Huh? But here you see that there's a pattern, and there's a pattern for this kind of vector right now. So this might be explained because we have this kind of pattern that's maybe just one vector is enough for this, and it's outperform. If you just keep increasing the other dimension, then you'll get bad performance for that. All right. So this is just my kind of thinking. So maybe yeah, for this kind of a recon, like the just digits reconstruction, maybe just q equals 1 is maybe the optimal values. All right, so, well, I don't know. Let's just continue. Huh? We already spent 1 hour already. So let's continue. Next question. So what should the reconstruction is q equals to 56? What is it if we actually try it? Okay, this is kind of easy. So we're just gonna go here, and then we just try this. Okay. And then I think here you need to also kind of like get the RMS value, right? So I'm gonna just copy this code here, just append this one from here. And okay, so this is the case where you have q equals the full vector. So let's see. So it should be, where is it? Where is it? Okay, but anyway, let's just take a look at the RMS. I don't know where does this result goes to in this plot right now, but anyway, so let's just take a look at this RMS here. Yeah, I think it's just this part. It's just this. So RMS is now again equals to 300.3. So if you see this again, if you see the previous this like the reconstruction error array here, actually I think it's still bigger than the if you just pick the Q as a 1. And I think it's just like the saturation value for if you just continue, well, here is already 3118, and here you get 3064. So yeah, just like if you just keep increasing, it's just like you just decrease a bit. Okay. So kind of proving the idea that actually we are just getting good results if we just pick Q as 1. Okay. All right, and here the last one about this part. So use actually I have some questions. I didn't really fully understand what we should do here. So use the Matlab function CompSum to create a vector where the ith element is the sum, but of all, but the I largest values for, and I is from 1 to 100 to 55. Compares the first 50 elements of this vector to the vector of reconstruction arrow calculated previously. So we're gonna compare this from this values. So I'm not so sure what does this vectors means, like here this kind of expression. But let me highlight this. So you want to create a vector whose the ith element is the sum of all but the I largest eigen values. Okay. So what I first have the impression is that what you're gonna do here, well, actually you just needs to so let's see if the I equals to 1, then your first this vector, the first value is just 0, because you're gonna exclude the I largest value. If your I is equal to 1, then you just exclude the first largest value. So it's 0 in the beginning. And if I equals 2, and then it's just the first largest eigen values, because you're gonna get rid of the 2, the second largest. And if then goes on, it's like if you are I equals to 3, it's just sum of the first and second the largest eigen values. This is basically what I think it is. So what I did here, of course, I get this eigen values again from the diagonal from this matrix, and I sorted it descending so that I make sure that this eigen value is actually from the beginning is very big, but in the end is pretty. It's in the end is really like in the end is gonna be really small. And here I just use this CompSum eigen value. So I just use this kind of function, and I just get this. So here you see here, basically, yeah, like I said, the first one is going to be a 0. And the second is just the first one. And the third is like the first one plus the second one. So let me just quickly, let's just open this eigen value just to see whether this is correct or not. If let's just validate maybe the first tree. So did I run this already? The sum, yeah, I already run this. So here, so first is 0, that's correct. And the second one is just the first value, which is here is correct. And the third one is basically the sum of the first two. So there's 3.29 plus 1.74, which is correct, the 5.0350. So yeah, so basically I think this is probably this is what does this mean. Okay. So now you get this, you're gonna get this value. Okay, maybe I did something wrong. Now this is, I think I should get rid of this for loop right now. Or no, wait. Yeah. Okay. Yeah, I don't really want to, because this is because I was keeping using this. So yeah, I just minus this. Yeah, this should be the same. So here you already, the vector is already created. So this is just the internal process here. Okay. So basically, if you just plot this, the first 50 values, then you this kind of like very nice curve is basically what I'm gonna get. So here, so this is this plot, and compare the first 50 element of this vector, and to the vector of the reconstruction arrow calculated before. So actually, I'm gonna compare this and this. And what do you notice? Okay. So guys, so what do you guys notice? I don't really see too much. I mean, it's for hard, it's not so obvious to see what is going on. So
I don't see it here. Sorry.
Sorry, I just wanted to say it's a nice curve.
You mean this one or this one? The above one or the below one?
The below is nice and the above not so nice, more like an edge.
Yeah. But well, yeah, but maybe I don't know. Maybe we can plot those two in the same plot. Well, okay.
But here, pay attention, it's not the same axis. But the axes are not comparable.
Yeah, it's true. I mean, this is because this is just arrow. This is the reconstruction arrow. But here, I mean, never mind what we observed here. But here is actually give you a hint what you should observe, which is really confusing for me as well. So here, the last question should show you. Let me just really zoom in. So the last question should show you a very interesting and important fact: the square. So this reconstruction arrow induced by not using a certain principal component is proportional to its eigenvalues. Well, this is very confusing sentence. It's very complex sentence. And then that is why if the eigenvalues falls off quickly, really quickly, then the projecting onto the first component gives more error. Okay, this is explaining what we observe. Like if you, because of our eigenvalue is dropping really fast, and now actually the first few, well, let's say the first few components give very small error. For in our case, well, actually the first one is giving the smallest error we got. And because the sum of the eigenvalue that we are not using is not very large. Okay. So this may be explaining why if the sum of the rest of the eigenvalue is not so much compared to the one which you are using, well, you're probably gonna get, and it's dropping really quick. and then you probably get a better result if you just use the first few components. Well, I don't know if you guys kind of agree with that or not.
I was thinking that the more components you use, you are a bit doing overfitting, but still it shouldn't have so much increased error. That is a bit weird. I think we have sorted the eigenvalues, and if we then indeed leave out the most important ones, then you should get an error that is proportional to it. So I think if we plot the curve again differently, like if we plot the curve in the bottom right differently, then I'm just thinking. And if we would compare that one with a plot where we leave out the four most important components, then we should see a proportional increase in the error. Let's say if we drop the most important principal components, then we should see that error increases in the same way, something like that. So if somehow by using the indices we leave out the important ones, the highest eigenvalues, the vectors with the highest eigenvalues, then we should see that immediately reflected in the height of the reconstruction error. Or is this not logical?
Okay, I just really confusing about this. Okay, this arrow induced by not using a certain so it's an arrow which is not, it's caused by not using a certain principal component.
Yeah, so let's say that we have two important principal components. For example, one with value 5 and the other with value 4. And if we are not using these two important principal components, then we should see somehow that the reconstruction error, that it takes maybe something like the height of this two together, let's say 9. It will not be exactly like that, but it should reflect it somehow. Like in the same way, if you would leave out 4 important highest components, then the reconstruction error should increase even more, and we should be able to see that in a curve. But I didn't do that part of the exercise yet. Maybe I'm very unclear, or
I mean, it's fine. This part is really, I think it's just, well, I think it's really confused right now. It's like not so, kind of have some all of a logic going on here.
You're clear, but this, the writing is not.
Okay, so let me just keep. Okay, maybe this part I don't understand, because this is basically, so let's say this part, like this one. So you are constructing this vector. Okay, this vector is something let's say, but maybe I was wrong about this this vector. Okay, so here you are saying, because the very first arrow we are getting here, this arrow is that, because now it's actually talking about this, okay, if you are, it's talking about the arrow which is introduced by not using a certain principal, like component. But maybe here I was something, I think wish here, because here I think I have a question about this. So this vector, the ith element, is the sum of all but the I largest eigenvalues. Okay, so maybe this vector value should be like this. So when I equals to 1, so you're gonna get rid of the, so it's actually your sum of your whole eigenvalues minus your first, like when I equals to 1. So it's your sum of your all the eigenvalues just minus the first, like the largest eigenvalues. Okay, and when I equals 2, and then the second element is actually the sum of the all but the first two largest eigenvalues. So yeah, maybe because I was confusing about this, but maybe if we change this kind of like definition of this sum largest eigenvalue things, so you want to actually first you want to but let me think about how actually we should really do this. So actually, so basically the first element should be the sum of all the eigenvalues, but except the first largest one. And then when I equals 2, it's just the sum of all the eigenvalue minus the first largest one and minus the second largest. So I think this may be making more sense right now, because I'm confused here in the beginning.
Yeah, I think if you go with the mouse, can you go back to eigenvalues and then the numbers appear? Okay, you had them. Okay, these there. If you subtract the 3.29 and you also subtract the 1.74, then you get the sum of all the, let's say, irrelevant eigenvalues of the less important ones.
Okay.
It's just a suggestion, but let's see what it does.
Okay, so yeah, I need to do some now. There, yeah, this is very hard math, huh? This math is really hard. Okay, so here, this is the sum. Okay, so this is basically sum of these all values, huh? So this is first, and this is eigenvalue. This is we are sorting. We're already sorting from the largest one to the smallest one. And this here, I mean, let's get rid of this for loop right now. Let's just comment this out. Let's just comment this out. Come on. Where is your comment? Comment this. Okay, if I don't do this kind of subtraction, so if I just like comp sum this eigenvalues, so it should be something like, let's just plot this and see what happens. And you see here, well, you start with something, it's pretty much the same curve, but now it's going somewhere. But here we actually, well, you want to, so we actually use the sum of all the like the eigenvalue, and we need to basically here we just, when I equals to 1, we actually want the sum of all the eigenvalue minus this one. Okay, so maybe in the end it will end up something, well, but it's just different. I mean, it's just something I can imagine it's just something like vice versa, like this. Huh? But let's see. So it's a vector, and then let's say the sum. What is the sum of the order? So sum values, sum of the all, and this just should be just like this, right? Values. Okay. Yeah, maybe just run this just to be sure. Okay, so this is the sum of all the eigenvalues. So what are we gonna do here is actually, but how do I do this kind of subtraction? Because this one is already a vector. So can we just do this? Because I know that in Python you can do that. Like you just basically, you just copy this, and then you just saying like, and you just equals to this sum values. This is a double, and you can directly try. Let's just try directly subtract this. Okay, I don't know if this is gonna give it any error or not. Let's see. Okay. Well, yeah. Well, it's a. So the arrow. So what are we gonna is seeing here? Okay, this is not. We are getting that. So this here is actually the value of which the one which I'm not using. Okay, this is like the value which we are using or we are not using.
We are not using it.
Okay, now I'm really sorry. Now I'm not just getting confused already. But see here, I mean, maybe we can forget about this part. I mean, in the error part, forget about this like q equals to 1, because this is something quite interesting. But here, if you see, okay, it's kind of making sense that this is doing some kind of like curve of, like going down, and it's those kind of curve follows, this like the similar pattern, like it's just doing this kind of nicely going down. So here you see some oscillation here, but well, it's making, yeah. Okay, now, yeah, I think now it's maybe making more sense. So the square reconstruction error induced by not using a certain principal element is proportionate to its eigenvalue. Okay, so basically, yeah, it's saying that, okay, let's say at this point, it's point here, it's proportional, and then here it's kind of proportional. Well, you can see that, yeah, proportional means, well, it's just like something decrease, this one decrease as well, something increase, this one, the corresponding one increase as well. But indeed, but we still see some oscillation. But the general curve trend is like this. They are both similar. Okay. Wow. We already waste too much time on this.
No, thank you. I'm glad to have the session. So
Yeah.
Same for me.
Okay, so while I let you guys to, let's just stop wasting time here. I mean, maybe, yeah, for the others, well, because for the others, it's just, well, it's some code you just need to study. So I'm not gonna go so much detail like this. I'm just kind of quick mentioning some points that I think maybe it's interesting. Let me just, yeah, so I'm just, well, for this code, I will later also publish this code as well in the Notion page, so you guys can see it later on. Just to if you want to check, okay. And here this auto encoder. Well, you can just you can run this exercise first. This stock encoder digital classification. Well, it's just something you need to run. Well, it's like official. It's just the official I think tutorial code script. You just need to run it and just to spend some time on it. And in the report, you probably just gonna write what exactly you do for each step. So I already kind of like did kind of like some small version of it. So here, what is happening page. So I just summarize these things like this. And just drop the code as well. So it's like also the screenshot. So maybe you can do the same stuff. But maybe, yeah, but in your report, you're probably just gonna mention this point. I think it's sufficient enough. You don't have to like, come up with a screenshot or whatever. Well, I don't, okay, so, and the next one, well, after you did this, well, you need to run this script of this digit classification, which I think they write it. Well, the idea is basically you just actually first train the autoencoder you're gonna train an autoencoder model, and then you're gonna compare this with two neural network, like the normal neural network with one layer and two hidden layer. And you're just gonna do some play with around with the parameters and just to answer some questions. That's basically you need to do. Okay. So here you're just saying, okay, yeah, are you able to get a better result or whatever? How many layers did you use? Those kind of question about your hyperparameters. Okay, so and you explain why. So you need to go through some lecture notes on this. Okay. Convolutional network. Well, it's again you need to go through some example here or example code here, which is this one. Well, it's actually you are not actually training any model. You are just loading some existing models, like the CNN models, and you just need to answer some questions basically. So here you are just So you run the script, and then you need to first question is basically you need to figure out what is your you need to be really familiar with what's how do you say the kernel for the convolution, and you need to be really good know about the convolution, what is happening during the convolution, and what is happening during the pooling. So you need to be really you can really understand what is going on, like with some real example, because this one is gonna ask you like, okay, take a look at this, and if you think you need to, here is just the weights. So this one is already answered in the script, so you can directly find that. So the first layer is just observation of the like the edges or the corner features. And here is asking what is the dimension of the input at layer 6. So this, yeah, like I said before, you need to be familiar with what is going on during the convolution and or what is going on during the pooling. So because those kind of operation kind of like reduce the size of the like your matrix a bit. So but you need to understand, you need to be familiar like how is the calculation going on. Okay, so there's some very nice, I think I found some online materials on this already, and explain about how it's working. And so I don't know where's the link right now. I mean, I did write some stuff. Where's that link? This one? No. But anyway, I think you can find tons of like materials here, like just to explain, okay, what is the dimension looks like for each, like layers of convolution layers, and you can just see it. Okay. And and then what is the dimension of the input for the final classification of the network? Well, yeah, you can check it. You can just directly check the information, which is on the using that some command which is mentioned in the script. Okay. But there's some I'm not gonna say it right now, but there's you need to really, if you didn't go through the script, you just sit. You need to really go through it. Okay, and here there's a CNN digits m, which is again trying to run the small CNN on the handwritten digits again, and use the script to investigate some CNN architecture, try different kinds of layers, combination, different layers, whatever, blah 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 blah, and we just briefly discuss the results. Well, this is basically again, it's kind of like different configuration of the hyperparameters. So you just try different, this kind of a hyperparameter and just see what is gonna be your result in terms of like, let's say accuracy or errors or whatever, or speed. We can just talk about like we just did we did in the first exercise about the like the neural network, I guess. So yeah, so basically I think that's pretty much is it. Yeah, so this code is, well, you just need to, nothing really special about here right now, because well, yeah, there's not too much things to going on. You just need to read and understand what is happening in the last two parts. It's just the first part is actually taking, you need to really coding a lot. Okay. All right. Well, I think we can that's pretty much I want to share right now. So if you guys still have so if you guys still have some questions, so we can still discuss.
For me, it's clear actually. Thank you. Thanks a lot.
No problem.
Yeah, sorry. It's
I don't know, guys.
clear.
How's your guys' progress on this kind of like assignments so far? Because I was right now, for me, I was really occupied with other courses right now, and I just, like I said, those kind of workshop is just for just for building the code, just trying to understand the code first. We're not really going too much about the report or whatever serial like a question that we are going through. So yeah, like I said, let's maybe stop the recording right now. I think does anyone still have questions? If not, I'm gonna stop the recording.
No, you can stop it if you want. Yeah.